Thanks, Chris. I know that it's various parts of the day. It would be, it is always, if you don't know, it's always easier for a presenter to see more than his face in the room. So just a very brief call out, if anybody's willing to turn on the camera, will make my life that much easier, because this really is, there's no slides to really go. Well, thank you all very much. Just even a couple faces makes that easier. Appreciate it. Yeah, so we're getting started here. And really the theme of what I wanted to talk about today, and I'll go ahead and spotlight for myself. That way that makes it easier too. All right. So the title was Hyper-Parallelisation. And I wanted to showcase some of the things that I've done leveraging channel wires within the LabVIEW ecosystem. So when it comes down to channel wires using the Teams hands feature, could anybody, or I guess if you have used channel wires, could you please go ahead and raise your hand virtually by virtue of the Teams feature? I think I can raise mine just to kind of lead the charge a little bit. All right, so I'll give us a few seconds. But yeah, while y'all are still trying to raise your hands or not, I think that bigger question mark of, let's go ahead and, yeah, 4. So not too many. We've got a room of about 20 people, almost. So it's about 4. So it's at 20%. So 20% of us have used it. All right. So go ahead and feel free to lower your hands. And then the other one is, who here has never heard, who has not heard of channel wires before? Because I've got to figure out how much to very specifically go into details about it. So who has not heard of channel wires that's been in this room? By show of hands. All right. All right. So great. So that means that everybody has heard channel wires, and so I'm gonna blame Chris for that one. Must have done some different meetings on it, so appreciate that. And yeah, really, this is going to be just a dive, basically a show and tell of what I've got. So rather than continue to jibber jabber, let me go ahead and just, I guess, kickstart the screen and make this go. So let's go. That's up there, and probably, there we go. So there's Chris's head. I'll get that going on another screen here. And lastly, there we go. So actually, this is going to, yeah, actually, you know what? I'm going to start off with a Google image search here, as I am wont to do very frequently. And I'm going to open up something called, actually, let's see, Radio Companion. Has anybody here used this tool? Oh, come on. That shouldn't have done that. There we go. Use this tool called GNU Radio Companion. Not seeing any hands or, okay. So this is going to be a learning experience. So I'm going to do this GNU. Open up some images. So GNU Radio is a piece of software for controlling software-defined radios. GNU Radio, it's, you know, GNU open source product, and this is the radio tool. And there's a tool called the GNU Radio Companion that gives an interface that will look strangely familiar to a lot of us, but only in part. Let me see if I can find one. Oh, there's the Wikipedia one. Let me see. I can just open that in a new window. There you go. So there are blocks that have wires connecting each one of those blocks, and each one of those blocks, although you can't see what the text is, it's blurry for me too. I picked a bad image. But it showcases data flowing, or it's basically the data relationship between two things. And if I think I've got the one on my computer, we got lucky. Yeah. Here we go. So this is an illustration of something that is the USRP is a software-defined radio. It spews data at a computer. Like a software-defined radio at its core doesn't do much other than acquire RF signals off of you know, well, you probably can't see. There's a, you know, venerated antenna. I've got a few of them here in my office. But what it does is it can take that data and it can throw it to sinks, right? In this case, it's just going to display it in several different ways. This is a very simplistic, they call them flow graphs. But seeing something like this, and something that was probably a little bit more complex than the one I chose here, see if this one's a little bit bigger. There we go. This is a little bit better. Open image in new tab. This has got a little bit more going on with it. And I'm just going to kind of tick off the things that it is, right? This is a USRP source, so it's a source of data. This is a FIR filter, so it's filtering the data. It's a low pass filter. This is an FFT sync, so it's going to show an FFT on the screen while you do it. This is a squelch, so every time there's no power above a certain level, it's not going to show it. Another resampler, another this is an FM demodulator, so on and so forth. And eventually this plays the FM signal for the broadcast FM radio out over the audio system of your computer, right? Now, this is relational data. Now, when this flow graph actually executes, there's a scheduler in the background saying what to run and when. But you're probably not that many RF people in the room, just statistically speaking, I'm presuming at this point, right? And one of the things that you can probably figure out is it's probably pretty easy to figure out what's actually happening here, right? If we go back to what Jeff Godowski originally was aiming for with LabVIEW as a core, abstract away the stuff that doesn't matter so much so that you can understand what's going on. Get rid of the semicolons, all this, right? Get rid of the unnecessary complexity and show just what you need, right? And when I saw this diagram, and I've been in RF for a long enough time, but I haven't really used this, the GNU radio or GNU Radio Companion all that much, but I used it and I'm like, this is exactly what I want. And of course, there's a song from probably back in the 30s in the United States. It goes, anything you can do, I can do better, right? It's a line from a movie, right? So I took that same stance of, hey, I'm looking at this. I like this. How do I figure out how to make something like this in LabVIEW? And so thus birthed, if it loads fast enough, which it might not at the moment, because I just started switching over versions. Let's just give me a second here. Let's do this. LabVIEW Radio Companion. There we go. Path. And I'm going to do, there we go. That opens fast enough. There we go. So by no doubt, you're probably thinking, well, Norm probably did a thing. Well, one of the things that jumped out to me while this loads that I want to highlight is that the behavior, the difference, the thing that made all the difference in all of this is I realized that I didn't know how that program worked behind it, but I presumed each one of those loops was an asynchronously running operation. Because one of the things that happens in RF is we start dealing with like 20 mega, let's see, 20 times 4, 80, like 130 megabytes per second worth of data is nothing. That's child's play. And that's what, that's probably far beyond what a lot of people in the room who are doing LabVIEW and data processing deal with, once again, statistically speaking here. And so I realized it was probably pretty important for me to figure out, hey, if I want LabVIEW to do this, I need to have it do this processing as best as it can and as in parallel as it can with so many different things. So since everybody in the room has already seen that one, I don't need that. So one of the things that I really figured out was like, okay, if I want to prototype what this looks like, I need to have a bunch of asynchronously running loops. And so if I were to just get to the slap chop version of this, come on, Norm. Everything's going slower this morning. Come on, there we go. It's getting the channel wires. So what we will see once this loads is a graph in LabVIEW that looks exactly the same, where it has blocks of information that are going to look a little bit different. So for while this ends up loading and you're possibly a little confused, if you didn't know, when you see a sub-VI in a block diagram and it's larger than a sub-VI, what is that feature that we typically associate with? Anyone want to take a stab at it? It's a sub-VI, but it's larger than what we're used to seeing. Pop quiz, right?
Like express VIs.
Express VIs, yes, thank you, James. So exactly, and so express VIs are typically what you would end up seeing. But has anybody seen an express VI looking thing that isn't blue? All right, so I have, and you can too. If any of you have LabVIEW open right now, if you take any sub VI, once again, non-primitive, and I'm sure everybody's already got LabVIEW in the background because you want to be programming at the same time, right-click on that sub VI, and you will see it shown as a checkbox that says Show as Icon. And if you go ahead and you right-click on that, you'll have them look like this. Where indeed, these are just sub VIs. View as icon, right? So I have basically sub VIs at this point that are showing relational connections. And each one of these, as you can probably figure out, is just taking data in and data out, and it's just chewing on it, right? What is this VI doing? It's doing a single operation. Why the hell would you put a single operation in a loop and make it a sub VI? Because when I do, then it is operating in a hyper-parallelized fashion. This VI has nothing slowing it down at all. And that matters quite a bit because if you were to do any one of the, say, USRP examples, you'll see that they typically, and what do we as LabVIEW programmers typically do? We put our programs mostly operating the operational code, the real guts of the code, kind of in a single loop. If you're an actor framework person, you'll not uncommonly make multiple different chunks or different asynchronously running actors, but you'll usually give each one of those a little bit more girth, if you will, to them, right? They'll be, each one of those actors will be doing a little bit more. Normally, you wouldn't make a single actor to do this. Right? It just doesn't make sense. Why would you do that, right? But when we go ahead and do that, now, if you look at this diagram, there's no tall pole in the tent other than my processor getting in the way of any one of these operations. Now, for my FMD mod, underneath the hood, there's a lot of things in this that could be yet further parallelized, which I haven't done yet. Actually, this one, probably not, because this goes straight to DLL. Yeah, if I go in here, it's straight to DLL. So there's nothing that I could really improve on this one that's doing the FMD mod. And I just happen to know that because I know Modulation Toolkit. This is basically, for anybody curious, this is RF data in, complex data. This is audio out on the other side. So FM demodulation, right? But these are single purpose nuggets that exist out in the world for the purpose of making sure that I can take advantage of every single core on my computer without actually having to do loop. Because what do we do in LabVIEW, right? We don't want to go two-dimensional grow, right? That's the one thing that we know. We're all willing to accept as a best practice. If you have to have a diagram that's larger than an average monitor, make it scroll in a single dimension. If you don't know that, shame on you, Chris, for not having that beaten into their heads by this point. But yes, you would want it only visible or scrolling in one direction. That would be really, really hard if you were to take this program as it is and recreate it just using cues. Because as you've known at this point in time, I mean, if you get into the guts of what one of these fat wires is, it's depending on the type of node that you're using. But if I were to drill into this and I were to get down to where the actual data is, there you go. Right, channel. And eventually it turns into get data from Q, right? That's this type of channel. This is the streaming, high-speed streaming channel. There are other channels of other types that do different things, and we don't need to get into all of that. That's less important at this point. I'm doing something wrong. In any case, but really at the core of it, each one of these nodes is basically cue in, cue out. But what was the thing that I led this herky jerky presentation with? I apologize, it's not. This is the first time I'm trying to give it like this. LabVIEW, Jeff Kadosky, abstracting away unnecessary complexities, right? Everybody in this room, probably to some degree or not, could recreate this hyper-parallelized diagram, but what would it look like on the other side? You'd have to have, the management of the air wires and the cues and the obtain cues and then the usage of them. It would be untenable. It would not be desirable. Also, you wouldn't want to really show your diagram to anybody and try to guide them through it to teach them how to do something novel with LabVIEW, right? If we're all in this room, clearly we have some modicum of interest in getting other people excited about LabVIEW, whether that's the person next to us or the rest of the world. This as an implementation is extreme. I mean, that's really the problem is it already existed, right? It's like, somebody else already came up with this idea. So it's not really novel. I really, really wish it was novel. The thing that's novel is that this is scheduled. This is not a truly parallelized operation. So as simple or as possibly more complex as it can get, right? There's a lot more. I mean, this is the same thing. This diagram and this interface, like this is the palette over here, right? Just to kind of give you an idea. Look, they have a bunch of stuff for like decoding data from the National Oceanographic Atmospheric Administration, right? They have things for Viterbi decoders and stuff. They have so many things for, and this is a small list really of available things in the palette for doing radio work, right? Things that are much more suited for what people do with data that's coming from or going to a software-defined radio. The thing it's missing is advanced processing. The thing it's missing, it has a variety of user interface widgets, as they call them, that are actually some things that we don't have, but it doesn't have everything that we don't have, right? Or it doesn't have everything that we have, but the extra processing and the extra things in communication are not present in this interface. And so this is a very, like I said, if I were to run this, which I can route my audio through. Let me just do a quick look, see something's broken. Let's see. No active diagram. Let's go ahead and enable that. Let's hope that's the only problem. It is the only problem. Hot damn in the morning. All right, so we're in good shape. All right, so the VI is runnable, and I'm going to go ahead and tune it into 90.5 megahertz. Actually, we're going to do a simpler one first. We're going to do, let's see, spectral scanning. Let's see what you are. No, that's not the one I want. Let's do. Actually, this might be it. There we go, waterfall. So this is my way of having a VI that does this, that just does a bunch of different little things. And so I'm going to go ahead and tune into 90.5 megahertz. And then I'm going to go ahead and double check the bandwidth. I'm going to open up my bandwidth effectively to be, let's make it 5 megahertz. 5 megahertz, and there's a couple zeros here. There's that. I'm going to go disabled and delayed, and let's see how this works out. This may work out well. It's the first time I'm connecting to my radio for the day, so you'll have to bear with me. Oh, all right. Let's do that. Let's see. What did I lose? SDR01. Oh, do I not have you plugged in? Oh, I got it plugged in. Let's see. Let's see. Oh, hey, you know what, Chris? How much more time I got? I didn't even realize you got an agenda.
Yeah, that's cool. You got like 25 minutes. You had 45 minutes in total, so yeah, we're good.
Oh, okay. Okay. Thanks. Appreciate that. Uh-oh. My radio isn't working. Come on. Let's try that again. Good. No. You dirty rat. Okay, so that's gonna make all of these demos far less interesting. It's would have run it, like you said, minus the complete meltdown of children this morning, would have been an okay thing. All right, well, that sucks. Yeah. Okay, well. All right. Okay. Well, let's go ahead and just open up for questions while I try to pivot and think of what's the next best part of the flow here. Any questions from the room? And also feel free to raise hands. I am monitoring it and the chat.
Yeah, go on. What exactly have the channel wires given you here that normal Q wires wouldn't have done?
The short answer is nothing, right? Channel. Well, actually, because you could theoretically do all this with channels, or sorry, with Qs, right? Absolutely. But what would the diagram look like? Would the diagram be done in a way that it would be easy to understand what's happening? Would it be self-describing? And for instance, for anybody that knows how broadcast FM does its thing, there's the mono data at the low frequency, there's the stereo data at 32 kilohertz above it, and like the FM spectrum is actually worthy of its own presentation by itself. It's actually pretty cool. But I originally had a program that was there we go. That was this, right? This was basically my program. And then when all of a sudden I started doing all of the outputting to my audio data, right? My audio sync, this would go to my speaker. The part of the demo was I run this, you hear North American broadcast radio, probably breaking various FCC rules, whatever, right? But that would be the idea. Like I've done my FM demodulation, right? I've demodulated, I'm gonna visualize and output audio to sound, right? If you followed this, I'm going to take the spectrum and I'm going to go to it pops up its own little UI that shows a spectrum. It does the resampling down to what my audio card needs at 4.1K, right? It buffers to a very specific size. But how easy was it for me to add yet another parallel process in this system? Right? That's all it took for me to add an available process. And if I look, I've started to create my own block tree of modulators, signal operators, audio, network, right? I'm starting to recreate what some of those things are so that, hey, if you want to go ahead and stream this, get data from, no, that's not what I want. Let's do something else. Signal operators. Yeah, I just want to add another filter in the system. Or, hey, I want to take that audio data and I want to modulate it with ASK, right? It's going to do the buffer thing because it's the first time I'm loading these channels in LabVIEW 2024. But yeah, that's it. So to your question, what does it add that you can't do with the Q? Nothing theoretically other than a beautiful abstraction and basically a simpler way of working with something that would normally have a lot of added complexity to make that hyper-parallelization possible. All right, Craig, did that answer the question, or was that close enough, or is that what you were trying to get out, James, or who was that?
Yeah, absolutely. Thank you very much.
Yeah. Craig.
Yeah, I had a question about the channel wires and how they work with the sub-VIs. So each of those, because looking at those sub-VIs, obviously they're a bit different to what we normally look at, but each of those yellow boxes is a sub-VI, right?
Yep.
And you've got a channel wire coming in and a channel wire going out. Is there?
Yep.
When you're working with channel wires like that, and you've just got channel wires on that sub-VI, does that mean that the data flow is not waited? You're not waiting for data flow between the sub-VI, you know, the sub-VI doesn't have to finish before the channel Y gets passed to the next sub-VI. Is that how it's working?
100% correct. I mean, if you look, this is the one that does the meat. This is the one that's really getting all the data, right? It's a very simple state machine. I'm initializing, right? If for those of you walking through, right, it's get the reference, set the stuff up, and initialize, and then go to work, right? That's it. There's nothing glorious than that. And then what does work do in timeout? You know, well, let's just go ahead and go to that version of it where it's continuous or not continuous, right? But all it does, this whole purpose, get data, send a queue. That's it. And when you're dealing with a device like I've got a software defined radio here that is the size of a credit card. I think I have a credit card. I don't, but it's the size of a credit card, right? It's amazing. It's beautiful. But this thing has 0 memory buffer on it. So you can get 56 megahertz worth of bandwidth, or 56 mega samples per second of bandwidth. So that's 4 bytes. So that's 224 or so megabytes per second worth of information off of this little critter. And it has no memory. So you have to stream over your whatever your USB, this is USB 3 pipe is that fast. So if you want to have a program that never gets a buffer overflow, the only thing you can have in the program is get data and send it somewhere else and go lather, rinse, and repeat. So yes, this is the one of the heads of the program, you could call it, because it really is the driving force. And a lot of these things are, yeah, it's this is it, man. It's a while loop, right? What does a while loop do? It runs. It just keeps running. And the only thing that this guy does is takes in the data and it does a frequency shift on it. Which once again, whether you're not RF or whatever else, it does a mathematical operation, right? And it does it really, really, it can't go any faster, right? The only way that I can make this VI go faster is if I go here and I go subroutine, right? That's it. You know, chew up hog every thread that you can to do your job, right? But yeah, this sub VI basically runs one time. Right? It's a mind melter, right? That's what else? Continue that train of thought for a second.
So it runs through like normal data flow. It's passing the stuff from sub VI to sub VI. It's not running in a continual loop.
Well, the data is going from sub VI to sub VI. The data doesn't stay in that loop, right? It's data in, data out, data in. So there's the sources and then there's the sinks. What would be something that just takes data in? Oh, I'm going to take RF power and I'm going to display it on a graph. So there you go. There's my sink. There's the data. I transform it from a complex data set into power versus time, and that's it. Now my user interface stuff. I mean, let me see if I can open up the actual example to show you what kind of, pardon my French on a mid-morning, but it's a bunch of bullshit that they do to make this, let me see, RF continuous, to make this run in these examples. I hate them. But they are the simple examples that existed before channel wires, before queues, before somebody thought of, hey, how could I do this on 20? There we go. And here's the crap that they have to do to make that work. But I can guarantee you that once a second, there's a pretty reasonable chance that you're going to get a buffer overflow. Right? This is 100% simple, right? When people are saying like keep it simple, stupid, right? 100%. There's zero complexity here. It's extremely understandable, but it is not practical to transform this into something that actually does something more. Right? And in fact, usually that's why people get really frustrated, is because they start to try to do a thing. Oh, this looks easy in LabVIEW. Let me shove some other signal processing widget in here. Uh-oh, something's angry at me. Oh, sorry, it's an edit mode. There you go. Right, they'll take some signal processing. Oh, let me go ahead and send a filter in there. And then all of a sudden everything breaks. They get overflows out the wazoo. I mean, a lot of times these are students that don't understand LabVIEW. They barely understand signal processing. They sure as heck don't understand really programming at a deep level at this point, right? But when they all of a sudden they go over and they use something like the GNU radio, like, oh, this just works, right? The scheduler figures it out, you know, however it does, I don't know. But I was like, man, sure is easy for me to describe this diagram to anybody out there. Now, let me be very, very ultimately clear. There are some critical flaws in this implementation, right? Some of you may have already picked them out. We'll talk about them in a minute, but it's more because of limitations within using the sub-VIs as I've been using them here and how we could use it. I've been trying to, well, there's a whole larger story there that we can talk to a little bit later. So there's a reason that this doesn't exist as a core product or something I'm going to release out to the wild per se. So, but before I dive into any further, Thomas, you've had your hand raised for a while.
I forgot it was raised. If I'm honest, Craig's beaten me to I was going to ask exactly the same question Craig's asked. Go on. Well, seeing as I've got the floor, feel free not to answer this because I think I'm in the camp of never using channel wires before. Do you say that pink wire is a stream? I've been reading up on channels whilst you were talking. Do you say that's a stream channel wire?
Yeah. So if I were to take, sorry, yes, it is. This is the high throughput stream. So if I were to go ahead and just hop into any one of these nodes, let's do the buffer to size. There you go. So if I wanted to send, basically, if I wanted to monitor this data, one of the things I could do with it is I could provide a monitor of the data periodically by right-clicking a wire, create. Do y'all see that zoomed in? Okay, good, thank you. So I can go ahead and create channel writer. So I have a variety of different types here. The one that I was using that you see on the node here is the high speed stream, right? There are some features that are missing from it when compared to the stream itself. But long story short, that is the stream. But of course, if I wanted to just monitor the data, I didn't need every last record of it. I could do something like a tag. And then I could do, I'll do a write with abort. That'll do that. And if everything goes according to plan, it only takes a second. It's doing a bunch of LabVIEW scripting in the background to create this brand new channel type. Of course, the canonical types are already made, but they don't treat the complex data cluster as a canonical type in LabVIEW, for better or worse, and that's fine. But yes, that will create a node on the diagram that allows me to send data over, right? That's the idea of when you're looking at channels, the nomenclature is like there's no block here, right? That's the illustration that Jeff Kodosky and team went to do, is like, hey, let's just make it look as though it's going straight past the structure itself. So this normally doesn't take this long.
There's another question in the chat, but I was also going to say, just from the hardware perspective, would it be worthwhile just taking a 5-minute break for you to have a look at that, or is it something that you think is probably not recoverable in that time scale, and then coming back to it, or
to try to get it operational here?
Yeah.
Forget if I've upgraded recently. I can try to get it because you want to see it run. I do too.
Yeah, man.
We'll try to switch ports again and just see what it does.
We can all leave you alone for a little bit and go and get a tea or something and then come back.
That's true. Everybody is remote. You know what? Oh gosh. Do y'all do that? That feels awkward, but I'm willing to. I mean, I can try to dance at the same time if you just want to look at the diagram and ask. If y'all ask questions, I can try to make that happen at the same time. I just don't want radio silence while I do this.
Sure.
Go on, I've just got a general question that anyone can probably answer. Again, it's I've not actually used channel wires in anger. It looks like you've obviously got multiple in all your syncs. Go on, reading up on them streams effectively are just queues behind the scenes, as you said, but you've obviously got multiple readers of that queue, one in each of those syncs.
This is the node right here. This takes the data from one and branches it to two.
Okay, right.
So yeah, there's this at some point in time, if you truly want every last nugget of information to do that, then you need to do those kind of things. However, actually, let's go ahead and open up the other illustration that is typically a problem with people doing SDR in LabVIEW, and I will try, and this one should work actually better. So if let's talk about communication in LabVIEW. If I were to, yeah, we'll let this guy load. If you're doing true, like an actual, like I'm going to send data to somebody else. I've got a file on my computer, and I need to send that file to someone else. Typically, what ends up happening is, for anybody that knows communication, is that bit stream gets hacked and sliced up. It gets packaged into other little packets that are transferable over whatever secondary medium it might be going through, right? And so there might be other things added onto that signal. And so same thing, like I've got my whole chunk of data, I slice it up, I put packets on it, I modulate it, and then I send it to the thing that's going to take that modulated data and spit it out to the world. And then the same thing in reverse. I want to take my the RF data that I've got in, and I want to demodulate it, and then I'm going to have bits, and then I need to synchronize them, and then I need to go ahead and take each frame, and I need to pull my payload out of each frame and eventually reassemble it and get the data on the other side. And this being a UK-based audience, I think y'all will really, really like this next example, even if I can't run it. So there's a little Easter egg in here for y'all. I think actually I have my always compile like to the max because of some of the stuff that I work on at work. So that's partial. Hey, there we go. Fantastic. So this is an illustration of taking the Magna Carta. There's your Easter egg. Right? So there's the Magna Carta. I take that and I chop it up into individual bits, right? So now I have a stream of bytes. Is it even bytes at this point? No, it's bits, right? Boom. There's my bits. And then I take that data and I slice the data stream into payload size chunks, right? This is, basically it's just a queue and I'm just cutting out and I'm leaving the stuff in the background, right? We don't need to know it. Just trust me when I say, and I document. And also, these are labels on structures. Use them, love them, always better, right? Slice data stream. Okay, then I need to take that data and I need to frame the data, right? So I'm going to take my data stream. There it is. But guess what I'm going to do? I'm going to take my my synchronization bits and my guard bits, and now I'm going to frame my packet with that individual piece of data, right? So now this is my frame, right? So I had my payload, and now it has been framed, right? Next up, I'm going to go ahead and take each one of those frames, and I'm going to modulate that packet. So I've got bits in, modulated data out, right? This is the same thing that you were looking at on the previous diagram. I just don't have these as sub-VIs, right? Then I'm going to go ahead and take that data. I'm going to do a resample. See, I think I can do this here. There we go. Right, so I'm going to resample the data, but here's another channel wire here, interestingly enough. This is actually resampling according to what the my source, my sync actually has down here on the other side for whatever this resample rate needs to be. Where did that come from? Hold on a second. I'm jumping around, and so it's very dizzying. I apologize for this. There we go. Now we can see what we've got. So let's do this, and I'm not gonna zoom in, okay? But So I take this, I modulate the packet, here's the desired sample rate, and then here's the actual coerced sample rate back out. And so now I will resample that data, which if you don't know, in signal processing is an extremely costly process in terms of DSP. So to have this alone in its own separate parallel loop is extremely helpful, right? And then I have basically a mux that allows me to choose a source, whether or not I want to have a single packet of information. I want to have it continuous modulation. I want to make pulses. This is just a useful thing for the debugging stuff that I'm working on, right? So I want to make it do different things. And then, like I said, lastly, the last thing here is basically, hey, I've got my USRP. I'm doing that. But one of the things that you may have noticed as an NI person who uses this for test, I can also just very easily, to do that, flip over, and now I replace that block with, instead of USRP, ignore the fact that I haven't changed the label yet, I'm sending it out to a PXI-based RF instrument. Right? The whole rest of the program stayed exactly the same. I changed one block on it, and now I'm going to another instrument. I don't really have a hardware abstraction layer, not really, but it sure as hell was easy, And if I were to go ahead and take this one level further, hey, that looks kind of neat, Norm. And let me try to figure out why it's not running. Oh, yeah, hold on a second. Let me get this back to USRP. Enable a subdiagram. Hey, and it's runnable. All right, let's just quick see if it runs. SDR1, USB. Oh, it's doing its thing. Sweet. So I could do continuous modulation. So now this doesn't look as interesting because it's not FM radio, but indeed I am continuously modulating on the fly, albeit a very low data rate. It's only like 800 kilosamples a second, so maybe about a sample a second. But it is doing it continuously on the fly, and my radio is happy. So let's go ahead and stop this for a moment. Let's consider trying to use the other one. Uh-oh, come on. Because maybe that'll be a little bit more interesting. Oh, here, let me just show you what that version looks like when it's just as the blocks. Oh, don't make me hate myself. There we go. So here you go. I'm just going to get that out of the way. So that same VI that was very, very lengthy and had a lot of things going on to it. And you were probably, I don't know what's going on here, Norm. It's hard for me to understand what you're doing. I have to read your labels on your structures. How about now, y'all? Can anybody in the room not understand what this program is attempting to achieve? Are you not entertained? Right. So, I mean, there's, like I said, there's pros and cons with this approach. Most of it has to do with error handling and shutdown criteria. So once again, we can get deeper on that one. But this is doing the same thing, right? It's the exact same front panel. SDR01, USRP. Yeah, should be able to run it. There you go. As a minimum, you can see there's a little red light on there. Now, interestingly enough, I do have a version of this as well that does the demod. And if I shove another antenna on this, which I have across the room, please wait. All right, 4 antennas. Never enough antennas. All right. Joys of being an honest person. What I got here? So I'm going to do, I think if I just hook it on here. I mean, technically speaking, I don't need to have another antenna on it, but I'm doing it for funsies. Let's see. Maybe just cable them together. Come on. I should have known, but in any case, so yeah, when this ends up happening, you'll see I'm doing that same thing in reverse, and now I'm controlling it through. So, once again, probably no major surprises here of how it's going to go. And I will get let me just see if I can get my audio here. Let's do this. I'm going to do a quick sound check. This is actually going to be valuable. That way I don't blow out your eardrums when you hear something. So let's go here. I'm going to bring that down. You just quick check. And for anybody who's, let's see, come on. Everybody gets to see what kind of music Norm listens to. Let's play some blues. And where's my audio? Include sound. Are y'all hearing that? Is it too loud? No? Okay, perfect. Okay, good. Because I've done this before and people have basically blown out eardrums because I left things turned up too high. Okay. All right, so there's that. There's that. Almost done compiling, unless it needs more. But wait, there's more. All right, let's see. FM, audio, what are you missing? Let's see, it's broken. Huh. There's the extra channel wire that eventually showed up there that we could use to technically monitor the data as it was coming through. I'm gonna get rid of that for the moment. There we go. So let's go ahead and we're gonna try to do this. Actually, let's do the spectral scanning first. And we'll do 90.5 meg. And we'll enable the waterfall. So basically this is going to be, once again, this is a think about what you would need to have on a diagram to have even just 2 parallel loops running doing this, right? So let's just go ahead and run it and see what we get. Come on. Hey, there we go. All right, exactly. And let's do single analysis. And let's go ahead. And so there is my full spectrum. Let's do a quick auto scale there. So there you go. So now you can see all the FM channels, a variety of FM channels, I guess you could say, all doing their deal. And of course, because it's FM, the audio looks like the carrier modulating its frequency. That's the voice. And the center channel there is a talk radio. So you can see that there's an idle period when somebody stops talking and they give the person the floor to talk to the next person, as opposed to something like this channel right here, which is very clearly something music, right? This is audio, much easier to kind of discern, right? Each one of these is an FM channel. Now, this is just a waterfall graph for anybody who hasn't seen these before, right? This is nice. This is neat. This is helpful. And if I get this up to something closer to -20, there you go. Looks a little, anyways. And then what, negative? There we go. Yeah, those are a little bit more typical colors. But now let's go ahead and abort the system, and let's actually do the one that does the audio. And we'll go 90.5 meg. And do the same thing. Let me get this guy configured appropriately. We're going to bring this down to 500. We'll do 250K. We'll do 25K. And we're going to do continuous so it doesn't get herky-jerky. And this might work. Sometimes it gets a little bit. All right. So. Come on.
The IDF in Israel.
Spoofing sends signals giving pilots, ship captains, and anyone else using GPS false locations. Israel has said it was blocking GPS, but doesn't admit to spoofing. Jane Arraf, NPR News, Amman, Jordan.
This is NPR.
Give me a second.
The Senate will take the first step today, the impeachment trial of Homeland Security Secretary Alejandro Mayorkas. All senators will be sworn in as jurors early this afternoon. Mayorkas was.
There we go. Sorry. There's a volume knob on one of those panels. But yeah, so each one of these is a different user interface component. This is the full spectrum audio. This is the filtered audio. So basically you can kind of see the relationship there. Let me go here to, right, there's that there. This is actually the audio itself, the raw audio. This is the power versus time of the FM signal. And then of course you've got the actual, get this guy, there you go. So each one of these are individual user interface components running in their own effective program, right? Each one of these is its own separately running, asynchronously running, hyper-parallelized user interface component. But that's only part of the real meat, right? Most of the stuff that it's doing, well, I guess the FFT, all the spectrum ones, they're doing their own spectrum. So yeah, each one of those spectrums are doing some heavy lifting of the overall stream of information, right? It's hypnotizing. I can just see everybody's like, I wonder what they're saying, right? I'm with you. It's so hard to do this stuff and not get sucked in. But I'm going to go ahead and stop this for a moment. And everybody stops gracefully, maybe? Come on. Who did I miss? Oh, that one, sorry, the top level one's still running. Hey. So, all right. So yes, that was the illustration of that, that in action. This guy there. And then if I were to go over to here, I'm going to go ahead and try to transmit here. Let's see if this works. Modulated pulses. There we go. So now we have my pulses of information. And if I go over to not here, but to my RX demod blockwise, we're going to try this and see if I set it up right. We did. All right. So there's my bursts of information. And one of the things that I'm doing is I'm actually monitoring those streams. And apparently I've done something weird with the Magna Carta. I think, that's right. I'm not doing any burst detection at the moment. So let me go ahead and make it, yeah, it's the sync detection. Let me go ahead and, yeah, let me make it a continuous stream and we'll stop and start it so you can see the venerated, Magna Carta come through. All right, so I'm going to go continuous modulation. There's that. And let's try that here. All right, so we have text coming through at the bottom. It is not the Magna Carta completely. Something is a little screwy here with the text. You could do a quick reset. There's definitely some of the right text in there, I can tell you that. Let's just go ahead and stop it. Yeah, there's something that happened with the formatting, but you can see the death of a man who holds a lay fee of the crown, a sheriff, royal officer. You know, you can, so we got some extra characters in there. Clearly, I've screwed something up. I'm not removing this. This is probably the sync pattern in ASCII. So for some reason, I'm not removing that. Whatever, a bug that I've got in there at the moment. But you can see I'm clearly getting the data from one, transferring it to the other, and it's basically here's my USRP doing the same thing as it was before. And then I'm just basically monitoring the stream. And this is kind of how I've decided, hey, I've got this massive stream of RF data. Go wrong. Sorry. There we go. Massive stream of RF data going that way. But I want to see what's I want to effectively probe that channel. Well, unfortunately, probing a channel is slightly more convoluted than what you'd want. And also, if you want to have it always present on your diagram, well, what do, right? How do you tap off that signal just for the sole purpose of monitoring that stream? Well, I've created a little monitoring stream node, which allows me to basically pluck off every update period. Just go ahead and send the data from one to the next, but every so often, go ahead and pluck it off and send it to a tag, which is basically a glorified local variable, right? or a single element queue, single element lossy queue. Yeah, I think it's like a single element lossy queue, whatever, right? So that is my way of facilitating, hey, I want to tap into that stream. And this is what, and then now I'm going to go ahead and monitor the power versus time and the power versus frequency, right? Those were the nodes that we were looking at down here in the bottom left-hand side. So, but this, the reason that me even highlighting that little part of this journey to hyperparallelization and the LabVIEW Radio Companion essence is that I had to screw with the channel wires to figure out what works and what doesn't. We have a technology at our fingertips that can do so many unique and interesting things. And granted, not everybody in the world's using it. So not everybody in the world has encountered every last quirk, twist, problem, bug, right? We would trust our lives, and many people have in a variety of different ways, of the Q primitive in LabVIEW. Totally okay. You're always going to be okay with the Q primitive in LabVIEW. Channel wires, are you guaranteed to always be okay? I'm not going to say that. I'm not going to say bet the farm on channel wires, y'all. But I will say start playing with them. One, because you can do some very interesting things, whether they're for your side projects, for your own needs, even in projects themselves. Just don't bet the farm on them, right? But we have to start using them as like any technology in LabVIEW. I mean, who here uses classes in LabVIEW? Who here was around for LabVIEW, what was it, 2008, right? Or which one was it? Hold on. No. What was the one that nobody wants to talk about? Yeah, LabVIEW 8.0. That's right, LabVIEW 8.0. That's right. We've all forgotten about it. Who's been around now? LabVIEW 8.0 was such a terrible release because they integrated so many things, right? It's just a joke. We don't talk about it. We went straight to 8.20, right? But we started using the project, right? We used the tools. We used classes in LabVIEW, right? We've used the things, and things have gotten substantially better to the degree where we would bet our lives in a variety of different ways, or our livelihoods as a minimum, on a class in LabVIEW performing the operation that it's been programmed to do. And that's just a bigger part of a bigger story of you have a very interesting new tool within the data flow paradigm that you don't get in other languages, right? The idea of parallel processing in other languages, everybody and their brothers got that nowadays. It's no longer a cool thing, right? We can still do it easier in LabVIEW than we can do almost in any other language, but can anybody do where'd you go? Oh, let's get you. There we go, right? Can anybody do that in a hyper-parallelized fashion that easily? Right? This isn't just a diagram. This is the code, right? That's the essence of what LabVIEW has been for so long. Doing this, showcasing this, allowing all of these things to run as parallel. It's not impossible. There's other graphical-based things that .NET has been kind of coming up with. There's things that exist in the world. We're not the only ones. But unless I was eager to try to start to use the channel wires, explore how it maps or how it fits or how it doesn't fit within my given application, we're not going to come up with the new revolutionary implementation for how to do things. Let me give you a hint. The queued message handler, probably everybody in the room here uses those. That wasn't part of people's brain processing back in 2003, maybe 2002. No, let's see, 1, 2, 3. Sorry, I started in 99. In 99, right? The idea of the queued message handler in the form that we have right now was not common, definitely not commonplace between LabVIEW programmers, right? And even then, it's not part of the LabVIEW. There's no node for queued message handler, right? Somebody had to think that up. I've got a queue, I've got a program. How do I make these two things do what they do? These are, what's the word I'm looking for? Design patterns. Design patterns in LabVIEW are our birthright. We are the programmers that enjoy, love, and like to use this. And we have the ability to come up with different design patterns that are truly unique to LabVIEW by virtue of the ecosystem that we are. Sometimes those design patterns are to get around the fact that we're not a reference-based programming language, right? We're by data flow by wire, right? Well, we have channel wires. We have a variety of different types of things that are now possible, but we all have to start diving in a little bit and say, hey, what kind of, wait a minute, I have two things running in parallel. What would happen if I just, instead of having my program be, if I go back to that example, right? Instead of doing that, what would just happen if I left the program exactly the same, but basically did while structure. Let's just go ahead and get rid of these things. Let's get rid of that, put that there. Get that, right? Put that there. Let's just forget that, right? Create channel writer, and heck, it doesn't even need to be streamed information. I just want the tag information, right? I'm gonna do a write with abort. That might be the first time it creates it. So hopefully it doesn't take too long. Much more impactful, much more sexy if you show it the first. Y'all see where I'm going with this one, obviously. But shy of this, right? If we can just kind of cut this portion of the recording out, right? Cut. Right, you'll see how simple it is to take a program that has this like kind of herky-jerky behavior of, oh, I need to just why do I need to periodically do that? Well, because you don't want to get in the way of pulling the data. Oh, well, now you don't. I just have these loops off to the side for the sole purpose of, hey, just spin it whatever rate you want. You want to go as fast as possible, as slow as possible, and it reads exactly as you think. Right. That's why so many of us get attracted to LabVIEW, because we see the code as it's like, oh, that we're going to do this. And then the minute that we get to, hey, we want to do something slightly more complex. Oh, well, you need a queued message handler. You need to understand this ecosystem. You need to understand these loops and all these things. And we're so used to the idea, probably, depending on what level that you're at, of going beyond that. And I think that this is our opportunity, if I can push this essence of how this operates forward. Oh, can I not branch it? What? We'll figure that one out in a second. Hold on. Create channel reader, read with the board. That shouldn't take any extra time. There we go. And then there's my aborted. Great, constant false. And I would say that as you go down this path, you will find that you need to pay attention to the programming paradigm associated with, try this here. There we go. That's good. How to terminate loops with abort, without abort. How do you leverage these things? It's more, oh yeah. Close enough. And if I do, oh, why is it broken? Oh, need to abort. There you go. Yeah, that's a great example. You need to pay attention to those abort signals, because the canonical question in every user group is, how do you stop two loops, right? And so this is one of the mechanisms that you need to become more familiar with. It's a different syntax. There's different nodes. There's different ways of leveraging it. So you have to be willing to, don't create a second channel just to terminate the other loops, right? Stephen Loftus-Mercer and Jeff Kodosky, the two authors of this technology, went through a rigorous, routine of trying to figure out what extra inputs do we need on these things in order, like previous element. Why would you need the previous element? I don't need that right now, but I guess that could be particularly handy in terms of, hey, what data have I just pushed out to push this data in? Right? There's tools and there's features that we don't know how to leverage, but if I do SDR_01 and I tune it into, once again, 90.5 megahertz, there we go. And I'll turn off the auto scale there. So there's our FM station, and then there's our FM, basically No, it's not our FM data in any case. But this is our broadcast station that we are seeing here. Actually, let me go ahead and put DB on. There we go. There you go.
Awesome. That was really good. Nom. Really good. Nom. Like that. That's tons of. Getting a bit of feedback on that. I don't know why.
Oh, sorry, that's me.
Myself.
I think I still have my fancy stuff set up. There you go. That's probably better now.
Sweet. Yeah, that sounds good. Yeah, that sounds good. Awesome. Oh no, still getting it.
Oh, I'll just mute myself.
Is that better? No, still happening. No, still happening. I'll have to deal with it. Yeah. Oh, I can't hear you. There we go. I've muted you now, Norm, so I can't hear you talking. But you were muted before I muted you, so I don't know. But I can't hear myself now, which is good. But thanks very much, Norm. That was class. Like really good to see some practical stuff with that. I think for a lot of people, including myself, it was nice to kind of see some practical demos of that and seeing the value and the power of it really, and how far it could get you. So yeah, really appreciate your time and sharing that all with us. So yeah, thank you very much.